In this example, we're going to use the step-by-step method to find a v0 t for t that is greater than 0. Step-by-step method focuses on solving for the unknowns from the general solution of a v0 t that is equal to k1 plus k2 times e to the power of negative t over tau. And k1 that is a steady state value, k1 plus k2 is equal to the initial value of a v0 0 plus, and a time constant tau for a circuit with one inductor that is equal to L over RTH. RTH is a semi-equivalent resistance. Let's solve the problem. Step 1, for time t that is equal to 0 minus, we're going to find the current IL 0 minus. Before time 0, we have a circuit like this, and we know that IL 0 minus that is equal to half of the overall current, which is 2 amp. We get this from the current divider circuit, and the two branches have the same resistance. This is why IL 0 minus that is 2 amp. And step 2, we're going to find the initial condition. Find V0 0 plus. And over here we have to use the continuity property of inductors. We know that IL 0 plus that is equal to IL 0 minus that is equal to 2 amp. Let's draw the circuit again. At a time t that is equal to 0 plus, we know the switch that is closed. So we have a circuit like this. And this inductor will be represented by a current source. Since we define IL 0 minus flowing downward, we have a current source which has a current of 2 amp, IL 0 plus. And over here we have another current source, 4 amp, another resistor, 6 ohm. V0 0 plus is defined here. And since we know that V0 0 plus can be found from Ohm's law, that is equal to IL 0 plus times 6 ohm, that is equal to 12 volts. So we find the initial condition. The next step is to find a steady state value. Step 3, find a V0 infinity. And we know that when t goes to infinity, this inductor will simply become a wire. Let's draw the circuit again. We are looking for the voltage V0 infinity. We have multiple ways that we can solve for V0 infinity. You can use the method you learned from chapter 3, node analysis or loop analysis, to find the voltage. Or you can use the power source transformation from chapter 5 to solve this problem. So let's use the node analysis, since that is something most of you are very familiar with. Let's select this node as referent node. So this node will become our V0 infinity. So we write a KCL at this node that gives us V0 infinity minus 6 volts divided by 6 ohm plus V0 infinity divided by 6 ohm minus 4 amp plus V0 infinity divided by 6 ohm, that is equal to 0. So we can find the solution V0 infinity that is equal to 10 volts. So we find a steady state value. The next is to find the time constant tau. Since this problem only have independent power sources, we can find our RTH by setting the power supplies to be 0. So we have, and this voltage source will be replaced by a wire. This is where we are looking for RTH. And this current supply will become an open circuit. We also have another 6 ohm over here. So we can find RTH that is equal to 6 plus 6 in parallel with 6. So that is 9 ohm. Now we can find a time constant tau that is equal to L over RTH that is equal to 4 over 9 seconds. So step 5, we can draw the conclusion. We know that K1 that is equal to V0 infinity, which is equal to 10 volts, and then K1 plus K2 that is equal to V0 0 plus that is equal to 12 volts, and the time constant tau that is equal to 4 over 9 seconds. We can solve for K2 that is equal to 12 minus 10 that is equal to 2. So V0 is a function of t that is equal to n plus 2 times e to the power of negative t over tau for t that is greater than 0.